on this one. From here on, we are recording this session. Okay. Let's see what else we need to talk about. Okay. So so today is the last class of the term. And the goal today is to just review a bunch of things, answer any questions you have about anything and everything that you might want to talk about. And then on Thursday, we have the test is going to be available in 2 distinct times. And I really don't mind if you guys want to do it earlier or later. We're going to run the test from 8 to 9, and then again from 10 to 11. And you can come to either one depending on which one you prefer. So 10 probably would be better since that's your class time and everything, but either way is fine. So let's go ahead and so the test is on Thursday. It's going to be 50 minutes. It starts either at 8 or starts at 10 o'clock, and those are the time. What's going to be covered? So what will be covered on the test is, I'm just going to go there so you can kind of see it. So what's going to be covered there is going to be chapter 4 through chapter 6. Now, I realize that part of chapter 4 was in test 1. And then there was a few folks who kind of, I feel like they were rusty on that. And there are some concepts in there that are critical, probably the most important concept in everything we've talked about. So I would like you guys to kind of have a better understanding of some of those. The stuff I'm talking about is like the call, return, stack, interrupts. You're going to run into these, even if you're just a purely high-level programmer, you're going to run into these concepts over your career, even if you never do assembly language again. So it's good for us to review it one more time. So that's going to be on the test as well. So just wanted to make sure that got clarified with everybody. So it's going to be everything from chapter 4 through chapter 6 that is in there. Probably is going to be 10 to 12 questions, depending on how it plays out. If you've done the homework quizzes and the labs and you understand them and you reviewed them, and anything you didn't understand you worked with, then I feel like you'll do really, really well, and 1 hour would be more than enough time for you to complete the test. Okay, it's not going to be a time race. But if you have to look everything up and relearn everything for every question, 1 hour obviously will not be enough. Okay. Having said that, let's go ahead and jump right in and start talking about specifically what concepts will be in the test. But before I go there, I want to kind of just wait a minute and see if you guys have any questions for me before we get going.
I'm happy with just a general overview, really.
Anybody else? Anything else you want to hear? Okay. So if there are no other questions, so let's go ahead and jump right in. So we'll just walk through, and I will use problems, example problems, to just demonstrate what's going to be on the test. So if you go back and look at chapter, if you look at chapter 4, for example, and you take a look at what is like the first thing we talk about there. And the first thing we talk about in that chapter, before we get into much of anything else, is stacks. And stacks is not a very complicated, but is a new concept. So you want to kind of think about it. Is that do you see my screen? Everybody see anybody can't see my screen? Okay. So stack is basically, think of an inbox, just a normal inbox that comes in, and think of every time you push. When they say you push something on the stack, if there isn't actually an instruction called push, whatever the address of the push is, let's say the address of push is 0, 1, 2, A. Or let me make it 8 because that's a complicated one. So the 8, and let's say stack starts empty, and every time you do a push or you do a call, something gets pushed in the stack. So if I do a push, what gets pushed on the stack is actually location 0x, not 128, but 12A. which is the next instruction, okay? Move. Move WF or whatever, 0x81 or something like that. Okay. Now, when let's say we come to let's say we come to 1, 2, A, B, C, and then let's say we have a call to a new function. Okay. So what happens here? So if then let's say new function is somewhere down here, x2948, something weird, okay? And we have a new function sitting in here. And so what happens when a call happens, then the address of 0x, not 12c gets put in there, but the next address, that's the one tricky thing you got to remember. The next address goes in there, but the next address is going to be 130. So 130 goes in here, okay? All right, so that's kind of how it works. And then when you do a return, when you execute the return, all it does, the first thing it does, it takes this address and puts it in the PC, which means now it's going to jump up here, and then it's going to take this out of here. So now the stack pointer had come up here. The stack pointer was 2. Now the stack pointer, which is a register in memory, is going to be 1 back here. And just the one thing is, every time in computer science we say it starts at counting at 0, here it starts counting at 1. So when the stack pointer is at 1, that means that's where it's looking. Let me stop. So that's kind of the call, return, stack pointer, and there's one other funny thing in there called pop. And all pop does is takes whatever is in the top of stack and throws it away. Okay, that's all that does. Now, once in a while, you get questions like, "What is the top of stack upper? What's the top of stack high? And what is the top of stack lower?" And 1 to A, so basically to keep the PC, which is what gets shoved on the top of the stack, is always program counter. It has to have 3 bytes to hold it. So the first 2 digits of hex is the lowest byte. The next 2 digits, the rest are trailing 0. So 0, 1 goes in here and 0, 0 goes in here. So if somebody asks you to do, which I will, that's what you want to put in here. Okay. Any questions? Anything about calls and return, stack pointers, stacks, any of that stuff? Okay. So as long as we are here, well, you might also get a question to see if you can kind of remember how to do the machine code for the call. And if somebody asks you to do that, they'll ask you, okay, it's the question, I think we have had it in the quizzes. It says, okay, what are the stuff if this is the call we are making, right? What will end up in program memory location 0x12c and 12d, and what would end up in location 0x12e and 12f, which, if you remember, call is actually has 2 words, right? 2 words get shoved in there. So it was basically asking you to find out what are the 2 words that are going to end up here. So what do? You go to your trusty sheet, the summary sheet, and you say, okay, what is a call? A call is 1110 and then 1100, and then what I have to do is figure out the K. The K is this is PC, right? This is the PC is going to jump to, so which is basically, if I break it up, it's going to be 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1 0 0 1 and 0 1 0. Okay. We know this is a PC. To make it a K. Oops. To make it a
I think
K. Yeah.
I think on that first byte you got the 1 in the wrong place there. Should be 2, right? So it should be the
Oh
second.
yes, thank you.
Yep.
1 should be here, 0 should be here. So basically this has to go away. So if you work this back out and like group them into 4, you'll see this will be a 1, this will be a 4, this will be a 2, this will be a so let's see. So 1 0 0 0 0 0 0 is here. This is the 2. What happened? That ended up being 1 0 1 0, which is a A, I think. And then this will be a 4, and this will be a 1. Okay. So that will become, and if you look at it really carefully, you'll see that this thing is this number divided by 2 because you got rid of the least significant bit. So what does that mean? That means 4 1 comes in here. The first 8-bit comes in here. So I'll write the hex in here. I know it's a mixed metaphor, but that's fine. And then down here is going to be A 4 1. And I think the second byte always has a 1 1 1 in front of F in front of it. Okay. So when they ask you what is in this location, which is the first word, and what's in this location, you write okay. And so the answer is that this will go in here, and this one goes in here. So you have E, C 4 1 in here, and F 1 4 A in here. Does that make sense? Any questions? So you'll see something either the same as what I just did, not same, but very similar to what we did here. And these are, we've had them in the quizzes, we have them in here. Any questions?
Yeah, I was hoping we could do one more about the whole stack thing, because I did have a lot of trouble when we were going over that, and I'm not really sure I understand it very well.
Okay, let's do another one. Okay, we'll do it from a different angle, so you get a different perspective. Fair enough. So let's go ahead and clear the canvas so we can start again. Okay, let's say somebody gives you a big stack. They say, okay, you're starting the whole process, and this is your stack, and in your stack you got a bunch of things. Let's say you've got and everything is in typically we write in it hex 298. Then I've got a 0x F284, and then I've got 0x220. Then I've got a 0x94, and let's say that's where we are. So I would like you guys to think about it and say, what if they ask you what is the stack pointer, what would you tell them?
Well, it's the top one, right? 0x94.
It's the stack pointer, not the
Oh,
stack.
oh, yeah. Okay.
So what would be the stack pointer? Other people can jump in. If you know the answer, you can jump in and help.
4.
4, because we've got 1, 2, 3, 4. So the stack pointer is 4, 4. Okay. Now at this point, you might kind of also come back and say, let's say at this point you're sitting here, right? I do a return. You execute a return instruction, right? Then the question is, what is PC? Let me know if I say something that doesn't make sense or you don't understand, right? So basically it says, okay, Somebody gave you this stack, it's got 4 items on it. And then at that point, the code execute a return. What's
It's
in
gonna
it?
be 94.
Everybody agrees with that? Anybody disagrees? with that?
Yeah,
Well, basically what he did is took the top of the stack, so he popped the top of the stack and said, oh, PC is that. What does that mean? That basically means that after return is executed, you're gonna go to location 94 and execute whatever command is in location 94. That's what PC means. Because then we're pointed to the next instruction. What happens to the stack? What happens to the stack is 94 is gone. 94 is gone. 94 is gone. Now the stack pointer is pointing here. So after this is happening, now the stack pointer is 3. Okay. Let's do one more thing and then we'll come back and ask you another question. We're going to do a pop. Let me use a different color. We're going to do a pop. We're going to execute a pop instruction. What happens?
Are you asking us?
Sure, go for it.
It's gonna just kick the top of the stack off.
That's it. Is it going to do anything else? Not really.
It'll move on to the next instruction.
Yeah, this is not going to do anything. Is basically get rid of this thing. The only other thing happens automatically is that the stack pointer now points here. Now we are down to start a stack pointer being 2. Okay, now I would, oh, by the way, you don't have to answer, but you want to take a few minutes and do it yourself, see if you can, if you get the right answer. Take a minute and see now what is going to be the top after here when we get, let me move this one up a little bit so we have room. So you've done all these things. You did the return, you did the pop. Now you're all the way down here and somebody asks you, what is the top of stack upper? What is top of stack high? And what is top of stack low? We basically they're asking you what's on the top of the stack. The 3 bytes make up the top of the stack. And you say, oh, look, there is 84, there is F2. So you do an 84 in here, F2 in here. And since there's nothing above that, those are 0, 0. Gavin, did that make sense?
yeah. It always just threw me threw me off how it cuts off the it doesn't include the whole value for everything, but I guess it makes sense now. We're in the TOS or higher and lower.
It's just basically because they can only store 1 byte in it, so you gotta just
Yeah.
good deal. All right, anything else before we kind of move away from this? These were more of the piece that is redundant from the last time. Okay, but there's one more thing. There's also going to be an interrupt business that it's going to ask you to fill in the blanks. You remember you had them in the quizzes. You're going to have to test it, just so you see if you remember that there are 3 interrupts. There are high priority interrupt. There are low priority interrupt. They start from a certain location. They end in a certain location. That kind of stuff. That's all it's trying to get you to think about. Also remembering that every interrupt has to end with a return from interrupt. Clearing the flag is important. Those kinds of things. Just so you can have it fresh in your mind. And I would say if I had to pick a few things that were the most important thing we've talked about so far, everything else is to support these ideas, is the interrupts, stacks, and how call and return work. All right, so okay, so now we get into the timers and the timing and all that kind of stuff. The other thing is to kind of, you most likely will have something, some little piece of code that you have to time or write a loop that delays for a certain amount of time or something like that. I'm sure you remember those from the lab and the homework in the class, but let's do a little simple one here. Let's say, let's write a delay loop and call a function and see how it works. So let's say we have a little function called delay, and you come into the delay and let's see, what am I doing? Let's put a constant. Let's say we do a move LW 25. Put a 25 in W register, and then we move WF to some register. Let's say it's 80, since that's our favorite. So we move 25 into 80, and then we have a little loop here. And one of the common things we do is decrement F. This is like a for loop, if you want to think about it that way. And then we decrement F 80. And I have to put the answer back in 1. And then we branch after long as it is not 0 to loop. Okay. And they come and tell us that, they could say uses a standard clock. If you use a standard clock, then the period is 32 microseconds. But sometimes we usually don't run it at the loop. That's too slow. Let's say we set it such that the oscillator, the period or the frequency of oscillator is, let's say, set at 4 megahertz. Okay. And based on our conversation on the time and all those kind of things, you know that means that the period of the oscillator is 1/4 megahertz, which is 1/4 times 10 to the 6 second, which is another way of saying is 0.25 microsecond. That means that the per cycle for instruction cycle, T of instruction cycle, is equal to 4 times T of oscillator. So each instruction cycle is 1 microsecond for this particular clock, right? It varies depending on what you do. So now I have to go back and see how many cycles does it take to do this instruction cycle. Then I multiply it by 1 microsecond. I have my answer of how long it takes. So I can go here and say, oh, here is 1, here is 1, here is 1, and here is 2 most of the time except the last time, right? Branch, as long as it's branching, is 2. So the question is, that means I'll go through this thing 25 times, except I got to subtract 1 from it, since the last time this one takes 1 cycle, and this is 2. So if somebody asks me so this is 3 times 25 is 75, minus 1 is 74, plus 2 is 76. That means this whole code takes 76 times 1 microsecond. So the whole thing takes 76 microseconds. Any question? Did that make sense? Did I go through it too fast? You want me to slow down or go back through anything? Okay, you're going to have something similar to this that you have to do. Just remembering, if somebody gives you a frequency, you got to do 1/frequency to get the period. That's an oscillator. Then multiply it by 4 because each instruction takes 4 oscillator clock. It's got to fetch the instruction. It's got to decode the instruction. It's got to execute the instruction. Then it's got to write the results out. So it takes 4 distinct cycles to get that done. Okay. Let me know again if you have any question. Otherwise, and then comes the timers. I won't go through this, but because we just did it recently, not too long ago. But unless you have a question, I'll be happy to go through it. So
is that a 76 you wrote? 76 times 1 millisecond?
yeah. So
Okay.
This is, I'm sorry. This is 76 microsecond.
Okay.
So the next one is gonna be timers. Remember, we have timers 0 through 3. This one you have to more or less go to the timer section because the summary sheets don't have enough information to work with. And so typically you have to pay attention to either a timer, let's say for 0, timer 0 low, timer 0 high. If you're doing 16, if you're doing 8, then you only have to worry about one of them. And then T0 control. This basically configures your timer. This one says where you start counting, and you're gonna every period. So and then you remember the calculation of tick duration. How long does it take for each tick duration? Would be 4 times T oscillator times any pre-scale they give you, and then any post-scale they give you. What happens if they don't give you any post-scale or pre-scale? You just put a 1 in there. And then number of ticks basically, if it's 16-bit, then you take hex value 1 0 0 0, and you subtract the value of timer 0 high low as 16-bit, right? You subtract that tells you how many ticks you need, and then you multiply those two, and it tells you the duration. So you're gonna have some question on the timer, setting a timer. Either they give you the value and say, okay, how long is the tick, how long is the duration, how many that's gonna happen, or the reverse, say I wanna set up this timer to give me a tick duration of this amount, and this is a number of ticks for this amount of delay, and you have to configure it. It goes one way or the other. Anything. So if these are the stuff from chapter 4. That pretty much wraps up chapter 4. I don't think we're going to do it too much with the UART and too much with the A to D converter and things like that. Those are very special features if you end up working on really low-end controllers and things like that. But the UART is pretty important, but most of the time someone else, you use a library to configure them, so you don't have to worry about it. Or in many cases, they're built into the operating system, so all of the overhead of that is taken care of by the programmers who are responsible for the operating system, for the BIOS, or whatever it's called these days. Okay, so the next one is the stuff around single precision and single floating point, a single precision floating point, and double precision floating point. So just there are either you're going to get a binary value or a binary or a hex value. In this case, you're going to get is 32 bits, or 8 hex digits, or 64-bit in this case. Okay, and then you have to give a decimal value equivalent. Either that's what you're going to be asked to do, or a reverse. So we have plenty of exercises to do that. So remember that when you go from here, you're going to have an exponent, you're going to have the sign, you're going to have the exponent, and you're going to have the float, right? Don't forget you have to add this to whatever the bias is, right? The bias for this one would be 127, for this one would be 1023. This one. And then that gives you 1 point flow with the F's times 2 to the power of exponents, okay? So and we have plenty of exercises in the notes. Make sure you go back and do the exercise and get a good handle on it, because we got to do a few of those, either a single floating point or double floating point, or one of each. Any questions so far? So that was chapter 5. Chapter 5, the only thing that's a big deal in there was that floating point, and just so you have an exposure as to what a floating point is. So now we are going to chapter 6, and chapter 6 is kind of like the, I don't know, the end, bring it all together type of a concept. But before we were able to do that, we had to introduce a new concept, and that was indirect addressing. So indirect addressing, we had three systems. We had indirect addressing 0, 1, 2. Did we have a 3? I don't know. I have to look it up myself too. I think there is only 3, right? How many you guys think there is? Let me take a look just to. Yeah, there's only 2, 3. Sorry, there's no. So there is only indirect addressing 0, 1, and 2. And almost all of them will have a base. You're going to have a base address, and the base address is called FSR, okay, with a number next to it indicating whether you're using a 0, 1, or 2. And what you could do, you can use INDF to go directly to the location pointed by this thing and start writing in it. You can use a post increment to access it, then increment the FSR, post decrement. You have pre-increment and all of those. So you have a bunch of these. And these are SFR registers. Remember, you don't write into this, you write into the memory location, data memory that is pointing to. Now, what are the tricky things here? So, and also the W register, there's a plus W register. This one doesn't change the FSR. So this one and this one don't change the FSR, but these 3 do change the FSR after they're done. So pulse W will take whatever is in FSR, adds whatever is in W register, and that's the location it goes to, okay? And if we're asking for the FSR value, we're not asking for the value in the memory it's pointing to. We're asking where is the base address at. Okay. Any questions? So again, once again, there are a number of different quizzes and homework and all that have you look at this. Make sure you take a look at them and convince yourself that you fully understand it before moving on. So that was indirect addressing. And then really the only other things we have here that we need to think about is this whole business of if I declare a variable, in C or another high-level language, Java or whatever you got going. Where in the memory do they end up? Okay, and we've spent a little bit of time talking about it. We commonly have a character, integer, float. We can organize them into arrays, organize their structures to structures of arrays or arrays of structures or both. So you're probably going to be asked to kind of think through this. And let's say you've been asked to take a look at a program and see what data it is saving in the memory. Maybe there's a security breach or something, and they want to know if there is somebody else messing with the memory other than our program. And we don't trust the software, so we need to actually look at the memory, see what's in there. So in those cases, you say, okay, let's do it. This one probably worthwhile since it's such a recent thing. It's worthwhile doing a quick example. So it could be, for example, let's say I have a character, and the character is, let's say, location, northwest, I don't know, let's say it's an array of 10, talks about which location we are at. And then you keep a structure which basically tells you a couple of things. Oops, I got carried away. So it's a struct, and my struct, let's say, let's say we are doing a GPS, so it's got a long, and this is a float, a launch, and then lat. So we have two floats. One tells us the longitudinal, one tells us the latitude. And most of you guys are familiar with that. If you're not, just do a map and click on a map and get the longitude and latitude. And those two numbers tell you exactly where you are on Earth. And then you can have also a character string of maybe a description. And let's say that's 100. So this is a, let's say you're writing a program that goes through and for various location, has the name of the location, has the GPS of where that location is situated, and has a description. This is a great place to go kayaking, or this is a great place to go, I don't know, something. Or here is where the store is at, or whatever the case might be. So that's kind of what you're doing. And they tell you that the memory location allocation starts at 0x10. They can tell you wherever it starts because the operating system is kind of the king of the road and can tell you where it is. So they could give you this, and then they could I could ask you to tell me, well, let's make it more interesting. Let's say there's 10 of these guys.
Actually, a quick question.
Sure.
Maybe you already covered it. Float, is that going to store the same as an integer?
No, float is the single floating point.
Okay, so just 1 byte.
How-
Or you're talking 32 bits, so it'd be 4 bytes.
Yep, 4 bytes.
Okay. And an integer would only be 2 bytes though, right?
Integer in this computer, integer is 2 byte. Yep.
Okay, so it's basically double that. Okay, thanks.
Floating. So let me, if you've never seen this, this is pretty amazing. Actually, I still am amazed that this works. I understand how it works, but it still amazes me. So you can go and let's say Clark College. And we can go to the mapping. And I want to meet somebody for whatever reason. I want to meet somebody, but I want to meet somebody right here. So I can literally get this GPS location. And when I enter it in any of the mapping solutions, it precisely tell me where we were supposed to meet or where that location is. And it's pretty amazing. The accuracy is absolutely amazing to me. But see, this float probably is a double, frankly. I just yesterday I was playing with this one. It's pretty amazing. If you remove the accuracy, watch what happens. So I think 3 is pretty good. 3 doesn't make it move. So remember, health center, this is sitting in the corner of health center. See what happened? That accuracy, when I moved it, it kind of, so all this becomes all zeros instead of having the specifics. So I basically missed the location we were supposed to meet by, I would say 50 feet to 100 feet. So if I start continuing to remove this accuracy, then my location is less accurate, just like floating point. We talked about money and other things, but this is a case used in GPS to precisely locate you. So if I had an integer is pretty bad, of course. Integer puts me, I mean, it could be hundreds of miles. If I only keep it as integer, it doesn't even assume. So probably put us somewhere in the middle of state of something. Let's see where it puts us. Yeah, middle of Oregon. Because if I make this a 6, it puts me, if I make it a 6, it probably puts me in the middle of Washington. Anyway, I'm getting sidetracked, but you gotta get the idea. So floating points are pretty important. Yeah, a little further now. So that's 1 degree of latitude. Took me from Salem all the way up to almost Olympia. Anyway, get off this topic. All right. Any questions? So the question on, we're talking about memory location now. The question to you might be, what location in memory is, oh, I didn't name this struct. This struct would be, let's call this struct feature. So a potential question would be, memory location of feature 1 dot longitude. So it wants you to know where is feature 1 dot long located. And
No,
then
that's the first byte of the longitude, right?
Yeah, that would be, yeah, a very good question. That's an excellent question. So, because if you remember, long is 4 byte. So when they ask you where this is, they're asking you what is the base address, where is the 0th location. And in here, we're going to assume the way the memory is organized. If you have multiple byte, the least significant byte comes first, the next one comes next, and next, and next. In case they ask you specifically for something there. Any questions? Anything we want to cover? Are we good? And that's pretty much it. I think that we haven't really now talked about anything else. That's it. That's going to be your test too.
You know, and this has nothing to do with the test, but do you know if we're going to revisit this in other classes later, like assembly language and
Not,
stuff?
you know, if you take software engineering, maybe at some point, or if you take computer design, yeah, maybe if you take the organization, you might come to it in your junior year. And it really, if you're a computer science, it depends on, or electrical engineering, it depends on what you decide to specialize on.
Okay.
So for example, if you go to, let's say you do, even machine learning might hit this one because you might need some tight loops to do some stuff. I would think the only time in my career I've ever have to deal with is when things, when something went wrong and we couldn't using high-level tools. Then we had to really kind of roll up. This is usually sign of trouble if you have to slow down. Unless you're doing stuff like some of the cybersecurity stuff, they might get in there for the routers and all the other stuff. They might get into that, but generally,
just for more security kind of a thing.
Well,
like to know everything that's going on.
Yeah, usually in today's world, everything is so well defined, so well done. Unless you work, I mean, if you're a computer engineer, you're going to spend a fair amount of time on this one, okay? But if you're a computer scientist and you're looking at this kind of stuff, that means something has gone wrong pretty badly. Your tools have failed you.
Okay, so there's a lot of tools, because you've mentioned some tools out there, and so there's a lot of tools that really assist you in your job.
Oh,
for
absolutely.
debugging and all that. So
Absolutely, there is. So you think about it. You know, an average engineer of computer science earns a little over $100,000 a year. That's, I don't know what the numbers are anymore. Probably much higher than that. But that's the last data I have. That's about the numbers I see. So if you think about it, you work about 2,000 days a year. So if you take 2,000 days and 100,000. Every day that you work, and you're costing your company quite a $500-600 a day. So then they don't want you to spend any extra time. Oh, that's not it. That, you know, that's the salary they pay you. Then they have to pay you benefits. They have to pay you medical stuff. They have to have management and all that. So cost them twice as much as they pay you. So it's a couple $100,000. So that costs you about, you cost them about $1,000 a day. There's a lot of incentive to spend millions and millions of dollars on tools to make you more efficient. Because if they save you one day in getting your job done, that's $1,000, $2,000 they don't have to spend. So So yeah, there is huge number of debugging tools, there is huge numbers of analysis tools that are out there just to make people's life easier. Um,
Cool.
All right. I don't know where I was going. Okay. Yeah. So that's test 2. Today's our last day of class. So this is your last and final chance to ask questions. Well, actually, that's not true. You can come back and ask questions again. But anything you want to talk about before we call it good?
In terms of this question, our feature structure doesn't start until 0x1a, right? And then we
That
would
is
go.
correct. That is correct. So let's since you have a few minutes and you brought it up, let's walk through it. Okay. So your base starts at 0x10. Fair enough. That's where your memory starts. Your first location is 0x10. So for the first 10 location, you're gonna have location in here, right? That's not part of the struct. That's on its own. It's character, and there are 10 of them. So I would like you to think about it. Just don't wait for someone else to answer. Just think about it and tell me what you think is the first location for feature 0, right? First one is feature 0, the structure feature 0, the first item in the array. Very good, very good. So how about I got one answer so far of what that address is. I want the rest of you guys to think about it, because this is the kind of thing that might throw you off, because we keep going between hex and decimal, so you've got to get a little bit comfortable with that. I have 10 locations, but the 10 is hex. So what would be the first location of feature 0? You can go ahead and type in your answer if you want. Okay, so this would be 0x1a, because location has got 10 bytes, which is a binary, comes out there. So then the next thing you got to do, you really are interested in feature 1, which is the second element of this thing. So now you got to figure out where this is. So you say, okay, feature long, float long is 4, float lat is 4, description is 100. So you got 104. So I got to figure out what 104 is in either, I can 2 options. I can either convert everything to decimal or convert everything to hex. Those are the only 2 options I have. Because you cannot do half of it in one system and half of it in another system. So I'm going to take 104 and convert it to, and by the way, if you don't know about this, this is my favorite thing of this.
Why is it 104 and not 100?
108 actually, right?
Oh, okay. Yeah.
Because there's 4 and 4 and 100, it's 108. Sorry, 104 is incorrect. And then we go to this little calculator, and I'm going to say I want to enter decimal, and I'm going to put in 104, and 104 is 68 hex. So each one,
108, right? Is that
what's that?
108? Not
108.
104.
Jeez, it's 108. Thank you. 108. I'm glad somebody's paying. Oh, what happened here? Clear it. Okay. 108. 6C. So this is 6C in hex. This is in decimal. So each one of these guys is 108 or 6C. So I just add 6C to that one. C is 12, A is 10, so it's 22. 22 would be 6. Okay. And that is the location of the longitude. We just found it because the very first item in the struct is a long. So that means right here is when the longitude is. 4 bytes later is where the latitude is. But they asked for the longitude, so I don't have to go any further.
So if we're looking for lat, we just add 4 bytes to that. And
So it would be 8A. So the answer to this question is 0x86. All right. Any questions? Any other questions? Well, that's about all I had. So if you guys don't have any other questions, we'll call it good for the day and see you